Hello, thank you for watching this video. I'm Mohamad Latifian, and I'm going to talk about best of both distortion boards, which was also presented in EC'23 in London. This is a joint work with Vasilis Gkatzelis and Nisarg Shah. We are all familiar with voting. We have primarily seen it in political elections, but we are using it in our everyday lives too. For instance, when a group of friends want to select a movie to watch in a movie night, or a group of students want to select a representative committee, they can all use elections. But it's not always among people. Think of a recommender system like Netflix that runs several ML-based algorithms that each recommend a set of films. Deciding on the final recommendations and their ranking can also be modeled as a voting problem. Here I'm focusing on voting with ranked ballots. Let me introduce the problem through an example. Assume that a group of coworkers who have to work late decide to order some food. In order to choose a restaurant and the type of food that they are going to order, they run a voting with ranked ballots. The options are pizza, steak, Chinese, or falafel. So they ask each office member to submit his full ranking over these four options. Here, for instance, the first voter likes Chinese the most, then steak, then pizza, and likes falafel the least. A voting rule gets all these ranked preferences as input and must decide on the winner. The rule can select a single winner or give a probability to each option and output a distribution over them. We call the former a deterministic rule and the latter a randomized rule. The basic question in voting theory is how the voting rule should select the winner. What are the characteristics of a good voting rule? For instance, here, if we take a closer look, we can see that pizza seems like a good option. It appears as the first choice of two of the voters, the second choice of two, and never appears as the last. But is it really good? What is a good measure to decide on that? And what is a good voting rule? There are different approaches to address this issue. Some works try to compare different voting rules by comparing the set of axioms that they satisfy. But here we compare voting rules by the quality of their output. To do so, we use the distortion framework as a quantitative measure of comparing voting rules. First, let's talk about the utilitarian view introduced by Prokacia and Rosenshine in 2006. In the utilitarian view, we assume that the rankings of the voters come from their underlying utilities for the options. That means each voter has a secret value for each option and ranks the options in the decreasing order of their utilities. For instance, here the first voter has utility of 50 for Chinese, 40 for steak, 10 for pizza, and 0 for falafel. So he ranks the options as you can see. Having these utilities, we can easily compute the social welfare of each option and select the one with the maximum social welfare. But in reality, we don't have access to these utilities, and even the voters themselves might not be able to exactly identify their utility for the options, as it's much easier cognitively to compare the options. However, even if we don't know the utilities, we want a voting rule that guarantees some level of optimality on its output. So we don't have the utilities, we only have the rankings, but we want a rule that outputs an option or a distribution that satisfies some level of optimality even in the worst case of the utilities. Formally, we have set C of M candidates. I might refer to them as options or alternatives, and set V of N voters. Each voter I submits ranking sigma I over the candidates, and these together form the input. Sigma I stems from underlying utility function of voter I. That means candidate C appears above candidate C prime in the ranking of voter I if utility of C is at least as much as utility of C prime for voter I. A voting rule gets these preference profile, which is the set of all preference rankings, and outputs a distribution over the candidates. If the distribution always has a singleton support, we say that this rule is a deterministic rule. In addition, in order to make different voters' utilities comparable, we have to normalize them. To do so, we use the unit sum normalization, and we assume that the total utility of each voter for different candidates sums up to 1. With respect to a utility profile, we can define the social welfare of an option as sum of the utilities of different voters for that option, the optimal option as the one with the maximum social welfare, and the approximation ratio of each option as the ratio between the social welfare of the optimal to the social welfare of that option. So the approximation ratio is a value greater than 1. Finally, we can define the distortion of a voting rule as the worst case approximation ratio of its output. So the distortion is maximum over all possible utilities and inputs consistent with that utility, the ratio between the optimal social welfare and the expected social welfare of the output. But this is not the only way of thinking of underlying values of the voters for the candidates. There is another model named the metric view, which was introduced by Ancelovich et al. In 2018. The main difference here is that we assume that each alternative has a cost for each voter. So to see this in an example, assume that the same set of coworkers decide to go out and get pizza on weekend. They know exactly which pizza place is the best in their city. However, it has several branches, so they have to decide on the branch. Again, they run a voting with ranked ballots, but this time, since they live in different parts of the city and there is no other difference between the branches, each of them prefers the branch which is closer to their place of living. So they sort the option based on the distance. In this setting, each option has a cost for the voter, and the optimal alternative would be the one with the minimum social cost. Let's take a closer look. For instance, this voter looks at her distance to all branches and sees that branch number 4 is the closest to her, then branch number 5, 1, 2, and finally branch number 3. Other voters also do the same and submit their rankings. The metric cost assumption also makes sense in facility education problems or in political elections if we think of the political spectrum. Formally, again, we have set C of M candidates and V of N voters, where each voter submits a full ranking over the candidates. But here, instead of utilities, we assume that all voters and candidates are embedded in a metric space D, and candidate C, and if candidate C appears above candidate C prime in the ranking of voter I, that means the distance of voter I to candidate C is at most as much as the distance as his distance to candidate C prime. A voting rule gets all these rankings and outputs a distribution over the candidates. And here, with respect to a metric space, we can define the social cost of an option as sum of the distances to that option, the optimal one as the one with the minimum social cost, and the approximation ratio as the social cost of an option over the social cost of the optimal, which is the minimum social cost. So again, here, approximation ratio is a value greater than 1. Using that, similar to the utilitarian case, we define the distortion as the worst case approximation ratio of the winner determined by the voting rule. The difference is that here we get the worst case over all possible metrics, and inputs stem from that metric. Let's conclude our definitions by seeing the characteristics of these two words side by side. In the metric setting, we have negative values, but in the utilitarian world, we have positive values. So in the metric, it's cost. In the utilitarian, it's utilities. We have to add an assumption to these values to make the valuations of different voters comparable. In the metric setting, we have the metric assumption that says that all the voters and candidates are embedded in a metric space. In the utilitarian setting, we have the unit sum assumption. The objective in the metric setting is to minimize the social cost, while the objective in the utilitarian setting is to maximize the social welfare. And we define the distortion in the metric setting as the worst case ratio between the social cost of the output over the social cost of the optimal, while in the utilitarian setting, we define it as the maximum worst case ratio between the social welfare of the optimum to the social welfare of the output. So it's the same that in both words, the distortion is a ratio greater than 1, and the lower the distortion, the better the guarantee that the voting rule gives us on the optimality of its output. So as you can see from the title of this work, we are planning to think about these two types of distortion at the same time. But why? First, we can see that these assumptions are way too fragile. For instance, agents might care about features other than distance or their cost. The other thing is that their cost might grow nonlinearly in the distance. The problem is that if the distortion bounds strongly depend on these assumptions, we might not get good bounds if in many scenarios that these assumptions does not exactly hold. The other reason to consider both words at the same time is the fact that for elections, and especially large elections, we might want to use website or voting bots to run the election. The automated system doesn't have information about the context of the election, so it cannot decide whether it has to run a voting rule that works well for the utilitarian case or the one that works well for the metric one. So it's hard for an automated system to decide on which voting rule to use if it wants to get a good distortion. So if we manage to design a rule that has good distortion in both words at the same time, we can use it without knowing anything, without context, and be sure that we get good distortion bounds. Over the past 16, 17 years, there has been several works considering the distortion of different voting rules and aiming to design voting rules with optimal distortion. However, as you can see, voting rules designed for one word have awful distortion in the other. Among the deterministic rules, we have plurality, which selects the candidate who has the maximum number of top votes. It has theta of m squared utilitarian distortion, but in the metric world, it has theta of m distortion, which is way far from the being optimal. We also have Cold-Plant, which has a metric distortion of 5, but has unbounded utilitarian distortion. And we have plurality matching and veto, which are optimal in the metric setting and have distortion of 3. But their distortion in the utilitarian world depends on the number of the voters, which is not good. In the randomized setting, we have harmonic rule, which is almost optimal in the utilitarian world, but has unbounded distortion in the metric setting. We have a stable ladder rule, which is optimal, asymptotically optimal in the utilitarian setting, but has, again, unbounded distortion in the metric setting. And we have random dictatorship, which has metric distortion of 3 minus 2 over n, but has a utilitarian distortion of m, the square root of m, which is far from being optimal. So as you can see, none of the well-known rules have a good distortion in both words at the same time. So the question is that if it's possible to design a rule that gets the best of both worlds at the same time. In the deterministic case, we try to answer this question. We know that the best possible distortion, metric distortion in the deterministic setting is 3, achievable by plurality matching or plurality veto. And the best possible distortion is theta of m squared in the utilitarian setting. Here we design a rule called pruned plurality veto, and we prove that, and this is a simple rule that prunes some of the candidates based on a fixed constant epsilon, based on their number of their top votes, and then runs plurality veto on the remaining candidates. We show that this rule gets metric distortion of 9 plus epsilon, while having utilitarian distortion of m squared over epsilon. So we can asymptotically get best of both worlds in the deterministic case. But the question is, can we get exactly optimal distortion in the metric setting while getting somehow close to asymptotically optimal utilitarian distortion? We answer this question negatively and show that if we want any utilitarian distortion less than m squared, a square root of m, the metric distortion is strictly greater than 3. In the randomized setting, we know that the best metric distortion that we can get is 2.753, which is a very recent result. And the utilitarian distortion, the best utilitarian distortion is theta of square root of m, which is achievable by this stable ladder rule. Here we design the truncated harmonic rule, which finds an alternative with good metric distortion using a deterministic rule like plurality veto, and then selects a voter uniformly at random, finds the ranking of this candidate X in his ranking, the rank of this candidate in his ranking. And then for the candidates who appear above this one, we give them some probability that is in proportion to their rank in the ranking. And we give the a good portion of the probability to candidate X. We showed that this simple method gives us metric distortion of 3 plus epsilon, while having utilitarian distortion of order of square root of m log m over epsilon. So we can get asymptotically tight distortion bounds simultaneously for both words up to a log factor. We also consider the case where you only have access to top T choices of each voter. This might happen when there are a lot of candidates and ranking all of them is way too complicated. So here we show that here we know that the best metric distortion that we can get with having only access to top T preferences is theta of m over t, while the best utilitarian distortion that we can get with the deterministic rule is theta of m squared. Considering both words, we prove that it's not possible to get best of both words in this setting. We show that any bounded utilitarian distortion implies omega of m minus t plus 1 metric distortion, and we design a rule that gets order of m squared utilitarian and order of m minus t plus 1 metric distortion. So we show that getting best of both words is not possible with the deterministic rule in the setting that you only have access to top T preferences, but we design a rule that gets the best thing that's possible. In the randomized case with top T preferences, the best that we can get in the metric setting is 3 minus 2 over n, and the best that we can get in the utilitarian setting is maximum of root m and m over t. We show that if we want to consider both words, if we want to get metric distortion of dm, the best utilitarian distortion that we can aim for is omega of m square root of m over dm t square root of t. And we show that if we change the truncated harmonic rule that I described earlier to only use the top T preferences, we can get order of m over t metric and order of m square root of m log t over t utilitarian distortion. So as you can see, we have a gap here, which is an interesting open problem to think about. To conclude the talk, I want to say what we have seen so far. We see that the best of both worlds is achievable if you have access to the full rankings. It's not the case if you have only top T preferences. The bounds in the top T setting might be improvable, even in the setting where you have the full rankings. We have a log m factor that is very interesting if we can get rid of. We can also think of best of both worlds distortion in other settings such as matchings or voting with unit range utilities, and etc. The other interesting thing is to think of other things that has considered in one word in both simultaneously. So we can think of communication distortion trade-off or strategy proof rules that have good distortion on both words, and these are some interesting future directions. At the end, I want to thank you for watching this video, and I encourage you to see the paper for more details. And if you have any questions or comments, please don't hesitate to contact me, Vasilis, or Nisarg. Thank you for your time.